Hello, welcome to lecture 2 of the course. In the last lecture, we have started discussing the quantum mechanics of two-level atom or two-state quantum system. We learned how to write down the Hamiltonian of a general two-level system using the so-called Pauli matrices. Let us continue our discussion. In the last lecture, as we have discussed about a two-level atom, we represented the ground state of the two-level atom by this Kate Z and the excited state by Kate E, and they have energy. We have chosen the reference level such that the excited state has energy plus epsilon z, the ground state has energy minus epsilon z, and the arbitrary state of the two-level atom is written as a superposition of the ground state and the excited state Kz and Ke, where Az and Ae are the complex amplitude of the ground state and the excited state respectively, and the Hamiltonian we have written in this particular form. And as you can see from this form that this Hamiltonian is Hermitian, just like any operator in quantum mechanics, as we know that it has to be an Hermitian. Then utilizing the so-called Pauli matrices, this Hamiltonian for the two-level atom can be written in this very compact form, where epsilon is we are writing it as a kind of a vector, and sigma, which is the Pauli operator having components sigma x, sigma y, sigma z, which are the Pauli matrices as defined in this equation. Sigma x is 0 1 1 0, sigma y is 0 minus I 0, and sigma z is equal to 1 0 0 minus 1. So this is the stuff that we mainly discussed in the last lecture. Now let me make few comments about the matrix representation of the Hamiltonian. And already we have, though we have written the matrix form of the two-level atom, so I am going to now make some useful comments about it. Matrix representation of Hamiltonian, I will make some general comment, and which is going to be very useful for later part of the course. But let me first talk about the state vector of the general quantum system. You see, state vector K psi, which represents an arbitrary state, which can always be written as a superposition of the basis states or the eigenstates. So for example, suppose you are having a n-dimensional Hilbert space, then you can write it as a superposition of the basis states, say K1, K2, right, K3, and up to, suppose you have n dimension, so you will have C and N, and this I can write in a shorthand notation like this. K psi is equal to summation over, say, Ci K I goes from 1 to n, where this K is the basis state, i's are the basis state. And in fact, already, just to remind you, for the two-dimensional case, I have written Ket psi as Az Kz plus Ae Ket E, or I can even use this notation, say A1 1 Ket 1 plus A2 Ket 2, right? This is for two dimension. Now I am writing here in this expression here, I am writing it for a n-dimensional system. Also, you know that for different basis states, as you know, they are orthogonal to one another and normalize with itself. For example, here in this particular case, for two-dimensional case, you know that Kz is normalized with itself. So Kz scalar product is going to be equal to 1, and this is scalar product is equal to 1. But the ground state and the excited state, basis states, are orthogonal to each other, which I can write as Ze is equal to 0 and Ez is equal to also 0, because these basis states are orthogonal to one another. In fact, I can write a general expression here for any two basis states I and j. The scalar product ij, I can simply write it as delta ij, where delta I is j is the so-called Kronecker delta, and delta ij is equal to 1 if I is equal to j, and delta ij is equal to 0 if I is not equal to j, right? So therefore I can write, in fact, using this notation here, using this fact, I can find out this coefficient Ci when I am writing it, this arbitrary state is a superposition of the eigenstate. This coefficient I can actually work out, find an expression for it. To do that, let me name it as equation number 1. Let me multiply this equation 1 on both sides by k bra of j, okay, bra of j. So if I do that, then let me multiply the right hand side also, because Ci is just a complex number. So let me now here, let me take the scalar product with I. So this is what I will get. And as you know, this scalar product Ji is simply delta Ji, and delta Ji is equal to 0 if j is not equal to I, and it is equal to 1 if j is equal to I. So therefore I will naturally get it as simply Cj. I think it is clear to you. This implies that this coefficient Cj, I can write it as scalar product of j and psi, or I can write Ci is equal to scalar product of I with psi. Okay, so this is what we have. So now using this, I can therefore write this arbitrary state as a superposition of where I have Ci ket I. Now instead of Ci, let me just write, this is Ci is just a number, so, and I have, this is just a number here, right? I scalar product of I with psi, and this I, because it's a number, I can take it this side also. So if I do that, then I am going to get, I'm writing here I and psi. Okay, so now if you look at this particular expression carefully, what you are going to see that I can now write this quantity ket I bra I sum over I. This is nothing but an identity operator, and this expression is of immense importance in quantum mechanics, and this is a, in fact this is a name, and this is called the so-called completeness condition. And we are going to use this particular identity or completeness condition quite often in this course. So now let me go back to the matrix representation of the operator. So this operator H, now I can utilize, let me show the immediately how I can utilize this completeness condition to understand the matrix representation of the operator. So this Hamiltonian say H operator, let me multiply both sides on the left by the identity operator and the right by the identity operator, and then I can now write this identity operator as sum of say this ket I bra I, okay, and then I have this H here, and this identity operator, let me write it as sum over j ket j bra j, okay, and let me now write it in a simplified form. Let me take this summation here ij, and I have here I H j, and here I have j. So this quantity is nothing but the matrix element of the Hamiltonian Hij. So let me just write it here, it is Hij, which is this quantity, and I have Ij. So this is actually the matrix representation of the Hamiltonian operator. When we talk about the matrix representation of any operator, we necessarily we basically understand that we are talking about various matrix elements. Now, for example, in our case, when we have discussed this two-level atom, the Hamiltonian, as per this language that just I have discussed, its various elements are going to be of this form. So here say E here, the first element, and then first element, that means the first row, first column, the first element. Then this one will have EHZ, and here I have ZHE, and I have here it would be ZHZ. Okay, now as per our representation or description, the values of the various elements are as follows. EHE is epsilon Z, and EHZ is epsilon X plus, actually I have written it at minus, epsilon X minus epsilon Y, and I have ZHE is equal to epsilon X plus I epsilon Y, and ZHZ is equal to minus epsilon Z. So as you see, these are the diagonal elements and these are the off diagonal elements. Okay, in fact these off diagonal elements are zero if the atom is not interacting with any external agency, and if it is isolated and not part of. This is very important, so let me write it down. Off diagonal elements in the Hamiltonian elements are zero if the atom or the two-level system, if the atom is not interacting with external fields or external agencies. Okay, or say the atom is isolated or not part of, atom is isolated or not perturbed. So in that case, if it is so, if the atom, if our two-level atom is unperturbed, not interacting with anything, then the Hamiltonian would be simply epsilon Z 0 0 minus epsilon Z, and the diagonal element basically is representing the energy levels of the atom, unperturbed energy levels of the atom. So this represents the epsilon Z and minus epsilon Z are the energy of the excited and the ground state. We'll have more clarity will be there when we'll discuss interaction of atoms with external fields later on. Now we are going to discuss the geometrical representation of the quantum states of two-level atom or two-state quantum system. Here I am going to use the notation that is generally used in quantum information science. Now rather than using kg and kt to represent the ground state and the excited state of an atom, I am going to use K0 to represent the ground state and K1 to represent the excited state of an atom or two-state system. Before I begin discussing the geometrical representation for the quantum state of two-level atom, let me once again revisit the Pauli vector sigma, which has the component sigma x, sigma y, and sigma z. When I say sigma x, it basically means that it is the projection of the Pauli vector along the x-axis. Similarly, sigma y means the projection of the Pauli vector along the y-axis, and sigma z is the projection of the Pauli vector along the z direction. And also you know that x is a unit vector along the x direction, and we can actually write it in a row matrix in this form, row vector 1 0 0, and y cap is 0 1 0, and z cap is 0 0 1. Now if I consider an arbitrary point in a sphere of radius r, suppose this point P I consider, and in terms of the so-called spherical polar coordinates, which I am sure all of you are aware of, in spherical polar coordinate I can write x is equal to r. You know, this projection is simply r sine theta. Let me remind you that in spherical polar coordinates are r, theta and phi, right? And when we go from the Cartesian coordinate x, y, z to r, theta, phi, the relations are like this, that x is equal to r sine theta cos phi, y is equal to r sine theta sine phi, and z is equal to r cos theta. So these are the relations between the Cartesian coordinate system and the spherical polar coordinate system. Now we can actually define the coordinate of or the unit vector of an arbitrary point P, as I have depicted in this particular figure here, on the surface of the sphere of unit radius 1. Now here if I take the on the surface this point P is there, and the radius of the surface is this sphere is equal to simply unity, and then I can define an arbitrary direction n cap by this relation, right? Because r is equal to 1, so therefore this x component, x part would be simply sine theta cos phi, sine theta sine phi, cos theta. So n cap represents an arbitrary direction. Now we can ask, what about the Pauli vector? So if we ask this question, what about the Pauli vector? What about the Pauli vector components along this arbitrary vector n cap? Then you just have to take the projection of the Pauli vector along the n cap direction, right? So this is what basically you do when I ask, say, what is the projections of the Pauli vector along an arbitrary direction, and in that case I can write, if I just break it up into the, it's basically kind of a dot product, though here Pauli vector, as you know, its components are basically operators, and we can represent these operators in the form of matrix, which you were already So I can write sigma dot n cap as sigma x nx, sigma y ny, and sigma z nz. And then if I put these components, just let me write here that this is your nx, this is your ny, and this is your nz. Okay, this is your nz. So I can now write then sigma x is equal to sine theta cos phi plus sigma y is sine theta sine phi, and sigma z is equal to simply cos theta, sigma z cos theta, sigma z nz is sigma z cos theta. And as I know the matrix form of sigma x, sigma y, sigma z, then I can write this sigma n, the component Pauli vector components along the arbitrary direction n cap. So if I put sigma x, sigma y, sigma z, then you can write the matrix in this form: cos theta, then here you have sine theta cos phi in the second column of the first row, minus I sine theta sine phi, and here you are going to have sine theta cos phi plus I sin theta sin phi, and here you are having minus cos theta. It's very easy to do, and in fact I can rather write it in a more compact form. I can write it as cos theta, and this I can write it as sin theta e to the power minus I phi, and here I can write it as sin theta e to the power I phi, and here I have minus cos theta. So you see, eventually we just need theta and phi to express the component of the Pauli vector in an arbitrary direction. Now let me consider the two-state system, arbitrary state psi for the two-level atom or two-state system. Now as I said, now I'm going to represent the ground state as 0 and the excited state as 1, and I can write it as a superposition of say K0 and K1. Instead of writing AZ, I am writing A0, and AE I am writing A1. So this is the superposition state, and you remember that I can represent this K0 by this column vector 1 0, and K1 I can represent by this column vector 0 1. So with the condition of course that A0 mod square plus A1 mod square is equal to 1. Now because of this condition, what I can do, I can take A0 is equal to cos theta by 2, and A1 I can write it as sin theta by 2 e to the power I phi. As you can very easily see that if I take A0 and A1 like that, then I would have A0 mod square plus A1 mod square is equal to simply A0 mod square is going to give me cos square theta by 2, and A1 mod square is sin square theta by 2. By the way, if you have forgotten, let me just simply write that e to the power I phi is equal to cos phi plus I sin phi, right? So this is very much well known. So then what you see, effectively we can write any quantum state, and which is this two-state system, two-state quantum state, which is also known as qubit state. This state can be represented by this coordinate theta phi, and then I have cos theta by 2 K0 plus sin theta by 2 e to the power I phi K1, and in the form of a matrix I can write it as cos theta by 2 sin theta by 2 e to the power I phi. As you see, now this is a very clever way to this actually leads us to a very clever way of representing a two-state quantum system geometrically on the surface of a sphere. This is a great tool, and when we represent it on the surface of a sphere, this is known as the block sphere. So what happens is, okay, let me just draw a sphere like this. Suppose this is my sphere and this is the equatorial plane here, and okay, just let me draw. I have my x-axis here, y-axis here, and z-axis. Now depending on the value of theta phi, you see any point, it is a unit sphere, this is called block sphere, and unit radius, it has a unit radius. Because it is a unit radius sphere, and the surface, any point on the surface, any point of the surface is represented by coordinate theta and phi. So as you see, the trick here, because the quantum state is also represented by theta and phi, so therefore any point on the surface of the sphere is a quantum state. So I hope you are getting the idea. Now if I, depending on the various values of theta and phi, you are going to get different quantum states. For example, if I just take, say, theta is equal to 0, let me draw the coordinates once again here so that you can understand it easily. So here, let's say any arbitrary point on the sphere is this, and this is your theta, and then if I take a projection to the equatorial plane, then this is my phi. Okay, then now if I put theta is equal to 0 and say phi is equal to 0, this is going to represent which point? Theta is equal to 0, so this is your theta, this is phi, right? If theta is equal to 0 and phi is equal to 0, this simply represents this north pole of the sphere, and in that case psi of theta is equal to 0, phi is equal to 0 is going to give me, again you look into this expression here, cos theta by 2 k0 plus sin theta by 2 e to the power I phi k1. This simply gives you cos theta. Okay, let me just once again write it so that cos theta is equal to 0 by 2 you are putting here, k0 plus sin theta by 2, theta is equal to 0 you are putting, and e to the power I phi, phi you are putting to be 0, and you are having here k1, and you know cos 0 is equal to 1, theta 0 by 2 is 0, cos 0 is 1, so you have simply k0, and sine 0 is 0, right? So therefore you see that theta is equal to 0 and phi is equal to 0, it correspond to the, on the block sphere, on the surface of the block sphere, this particular point represents the k0 or the ground state, and in fact this particular point here, north pole, represents k0 or the ground state. And similarly, if I write, say, theta is equal to pi and phi is equal to 0, this corresponds to this particular point opposite to this point, the south pole, and it corresponds to theta is equal to pi, sorry, theta is equal to pi, and phi is equal to, say, 0, then you are going to have psi at theta is equal to pi and phi is equal to 0. This correspond to the state k1. Okay, and you can go on working, find out various different states depending on the value of theta and phi. For example, if I take theta is equal to pi by 2 and phi is equal to 0, now this particular point is actually this point, let's say this point A. This point A here, you see theta is equal to pi by 2, because if I take the projection of theta, you know, in the equatorial plane, its theta value is going to be equal to pi by 2, and phi is going to be, this phi is going to be equal to 0, and in that case the quantum state, the two level quantum state, theta is equal to pi by 2 and phi is equal to 0, if you put, then this is going to give you simply 1 by root 2 k0 plus 1 by root 2 k1. You see, this is an equal superposition of k0 and k1. So you see, this way you can represent many quantum states. Effectively, what I mean to say is that any point on the block sphere, on the surface of the block sphere, represents a quantum states, and this is the difference between the so-called classical bit, where you are having only 0 and 1, and in the case of the quantum states you can have superposition state of different kinds only the condition is that the amplitude coefficients, if you take the mod square, basically these particular conditions, a0 mod square plus a1 mod square should be equal to 1. This condition has to be satisfied, then you can take any value of theta or any value of phi, right? And this way you can represent any point uh, on the Bloch sphere represents a quantum state for a two-level atom, and it is effectively an extremely powerful tool to in quantum information science, and this is exploited quite heavily. And maybe in the later part of the course, when we'll do applications of quantum optics, we may again come back to this Bloch sphere formalism. I hope you have understood the geometrical representation of the quantum states of a two-level atom or two-state quantum system, that is the Bloch sphere formalism. In fact, we are going to do some problems in the problem solving session on this Bloch sphere formalism. Hopefully things should get more clearer there. So let me end this particular lecture here. See you in the next lecture. Thank you.